Hello everyone, today we will learn about mechanics of liquids. For learning content, you will learn about fluid at rest, pressure, Pascal principle, Archimedes principle, equation of continuity and Bernoulli's principle. At the end of this topic, students should be able to define pressure, state Pascal's law and its application, explain buoyancy and apply the Archimedes principle, consider cases of partially and totally immersed object in liquid or air, illustrate fluid flow, and you have to know how to use continuity and Bernoulli's equations. As for our first topic here is fluid at rest. The density of an object is defined as its mass per unit volume. It is a scalar quantity. Meanwhile, pressure is defined as the normal force per unit area. The SI unit for density is Newton per meter square. Let's focus on the diagram given. The force exerted by a fluid on a submerged object at any point is perpendicular to the surface of the object as shown below. The force exerted by the static fluid on the walls of the container is perpendicular to the walls at all points and increases with depth. From the variation of pressure with depth, we consider a thin element of static fluid with mass, as shown in figure. The element of the fluid is in equilibrium because the fluid at rest. Hence our force is equal to 0, you can apply the force and weight at the element whereby force equal to P times A. If the liquid is open to the atmosphere, thus P1 is atmospheric pressure par and P2 is a pressure P at a depth h below a point in the liquid. Therefore pressure minus atmospheric pressure equal to PhG. Here is an example on how to calculate the pressure with the depth. As you can see, the pressure increase with depth. The pressure is the same at any 2 points at the same level in the fluid. The shape of the container does not affect the pressure at any point in the fluid as shown in figure. One of the mechanism is the pressure gauge's open tube manometer. The pressure at points S and T equals because the level is same whereby pressure S is equal to pressure T. The pressure gauge's or mercury barometer is used to measure the atmospheric pressure. The pressure at points S and T equals, and the mercury barometer reads the atmospheric pressure directly from the height of the mercury column. The value of height depends on the type of liquid was used. 1 atmosphere 1 atm is defined to be the pressure equivalent of a column of mercury that is exactly 0.76 m in height at 0 OC with G 9.81 meter per second square. Now we will learn about Pascal's principle. Pascal's principle states that pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of its container. This principle is made use of in the hydraulic jacks and lifts, dentists' chairs and hydraulic brakes. A piston with small cross-sectional area, A1 exerts a force, F1 on the surface of a fluid. The applied pressure, P, is transmitted through the connecting pipe to a large piston of cross-sectional area, A, Pascal's law. The applied pressure is the same in both cylinders, so P1 is equal to P2. Let's see the example given. The cylinder L has a mass of 700 kg and cross-sectional area of 1000 cm2. Piston S has cross-sectional area of 50 cm2 and negligible its weight. If the system is filled with oil of density 0.750 gcm3, calculate the force, F, required to maintain the initial position. The solution here stated that the force is equal to weight, which is equivalent to mass time gravity. You substitute all the info given and calculate all of the value. The unit will be in Newton. As for pressure at point C is equal to the pressure at point D, hence by using formula P rho GH equal to PL. Hence you will get 159 Newton for force. Next principle is Archimedes' principle. Archimedes' principle states when a body is completely or partially immersed in a fluid, the fluid exerts an upward buoyant force on the body equal to the weight of the fluid displaced by the body. Consider a cylinder of height, h, whose top and bottom ends have an area, and which is completely submerged in a fluid of density Re. The pressure at the top surface and the bottom surface will substitute together to form a resultant force. The resultant force due to the fluid pressure on the cylinder is the buoyant upward force, Fb, and is given by Fb equal to F2 minus F1. The buoyant force, also known as upthrust. The buoyancy Archimedes' principle is applied to marine craft ship, submarine and hydrometer. Table below shows the common situation to apply Archimedes' principle, which is a totally submerged object and a floating partly submerged object in equilibrium. Here is the summary of the proof in Archimedes' principle based on volume of the displaced fluid, buoyant force and weight of the object. Let's see some example here. A boat with its cargo has a total mass of 1.2 × 10 to the power of 7 kg. Calculate the upthrust on the boat when it is in equilibrium and the volume of the boat below the waterline. As for the solution for A, you have to know that F is equal to 0. Hence, the boat has a weight force. Therefore, F is equal to mg. Substitute all the value given and you will get the force. As for the volume of the boat below will be equal to the volume of the displaced water, therefore, F is equal to rho GV. For next example shows a balloon of mass is designed to lift a load of mass 4,000 kg. Hence, find the volume of helium needed to lift the load. Consider the system in equilibrium, hence you will get the answer. Next we will continue with equation of continuity. The equation of continuity is a fundamental principle in fluid dynamics that expresses the conservation of mass in a flowing fluid. It states that for an incompressible fluid one with constant density, the mass flow rate must be constant from one cross-section of a pipe to another. For example, fluid flow. Other than that is streamline, which defined as the path taken by a fluid particle under steady or laminar flow. Consider the steady laminar flow of an ideal fluid with density along a tube which changing cross-sectional area from X to Y as shown in figure. By using the principle of conservation of mass, thus the continuity equation is given by a 1v1 equal to a 2v2. The product of V is the volume flow rate is defined as the rate at which volume crosses a section of the tube. Example 4 shows a pipe of diameter 5.80 cm contained water flowing with a speed of 15 cm per second. A larger tube of diameter 7.60 cm is then joined of the pipe. Calculate the speed of the water flowing in the larger tube and the water flow rate. Hence, by applying the continuity equation of a 1v1 equal to a 2v2, therefore you will get the velocity or speed at larger tube. While the water flow rate is given by delta V over delta T, hence substitute all the info given to get the answer. Next we will learn about Bernoulli's principle. Bernoulli's principle states that for an ideal fluid, the pressure of the fluid is low when its velocity is high. When its velocity is low, its pressure is high. Bernoulli's equation also states that ideal fluid undergoing steady flow, the sum of the pressure, the kinetic energy per unit volume and the potential energy per unit volume is constant at all points on a streamline. The Bernoulli's equation is an expression of the law of energy conservation, since it is derived from the work-energy theorem, and the Bernoulli's equation only valid for an ideal fluid because the real fluids are viscous and gases are easily compressed. This is the application of Bernoulli's principle on Venturi tube. We can apply the continuity equation and Bernoulli's equation after that. By substituting the equation 1 into equation 2, therefore we will get the pressure difference. For Torricelli's law, we have to consider a tank containing a liquid of density. R has a hole in its side at a distance, h1 from the tank's bottom as shown in figure. By using the Bernoulli's equation, we will get the Torricelli's law. Let us see the example 4, which shows the application of the Bernoulli's principle and Torricelli's law. The water flow rate can be obtained by equation of Bernoulli. By applying the Torricelli's law, thus you will get the speed of water rate flow. From previous calculation you also can get the distance by using formula from kinematic equation for vertical component. Other application of Bernoulli's principle is an airplane. Lift on an airplane wing is due to the different air speeds and pressures on the two surfaces of the wing. You can see from lower pressure to higher pressure from the diagram. A sailboat can move against the wind, using the pressure differences on each side of the sail, and using the keel to keep from going sideways, also one of the applications that apply Bernoulli's concept. Besides, a ball's path will curve due to its spin, which results in the air speeds on the two sides of the ball not being equal, therefore there is a pressure difference. Also use Bernoulli's principle concept. That's all for this chapter. Thank you for watching.